So today we're going to go our next step in chapter 8. Last time we talked about 8.1, so we're going to begin on 8.2 today. And again, the big overview is that chapter 8 is all about hypothesis testing. And so then in the first section, we talked about the basics of hypothesis testing. And that covers a lot. There was over 50 slides in the first section. And as you can see in this section, we have 47 slides. So this covers a lot too. However, once you begin to wrap your mind around the basic ideas of what a hypothesis is in statistics, then you can try to think about how to carry out a hypothesis test, how to go through that procedure, how to perform a test on one of the three types of parameters that we study and that we've been studying in statistics, namely the parameter of a proportion of a population, what percentage of the population falls into a certain category, a mean value for a population, or standard deviation for a population. And so we focus on those three specific parameters in 8.2, 8.3, and 8.4, all the while trying to talk about how to perform a hypothesis test on claims about those parameters. So today we're going to look at 8.2, testing a claim about a proportion. So the key concept is got a couple of slides to introduce to us. This section describes a complete procedure for testing a claim made about a population proportion P. We illustrate hypothesis testing with the P-value method, the critical value method, and the use of confidence intervals. The methods of this section can be used with claims about population proportions, probabilities, or the decimal equivalents of percentages. Okay, so let me focus on this idea for a second. So they're specifically referring to using the P-value method, the critical value method, and the use of confidence intervals in order to test the hypothesis. So I'm just going to give you my opinion. The P-value method is the more intuitive and the more naturally easy to understand idea. Whereas the critical value method is kind of close to the P-value method, but makes much less sense when we're using technology very easily and very quickly, as we are when we use StatCrunch. And the confidence interval method is also understandable, but again, the P-value method is more of a direct test of a claim. And when I look at the problems on our assignments, almost all of them, if not all of them, you can just use the P-value method. So we're gonna kind of see what they have to say as we go through this introduction about these other methods, but I'm gonna try to focus most of our attention on the P-value method. Even if you then want to also understand the critical value method and the confidence interval, even if that shows up in a few of our assignment problems. For example, the critical value issue did show up in our discussions and was involved in problems in 8.1. But now that we're looking at 8.2, I think the P-value method actually will work for most of our work in this section. And so I'm going to just emphasize that in order to better prepare and more properly reflect the expectations of the students. So having said that, my focus being on the P-value method, let's see what their second slide of the key concept is. There are different methods for testing a claim about a population proportion. Part 1 of this section is based on the use of a normal approximation to a binomial distribution. And this method serves us well as an introduction to basic concepts. But it's not a method used by professional statisticians. Part 2 discusses other methods that might require the use of technology. And since we are emphasizing the use of technology, that's not usually an additional burden to us because we are trying to have that be the default, is to use technology. All right, so they're talking about a subtlety about the use of the binomial distribution approximation, but I think that won't really serve us. It's a theoretical discussion. It won't serve us in terms of practicality. So look, I'm going to try to focus on the practicality of what a hypothesis test is, how to perform it, and how to do that using technology with an understanding of the concepts so that the results from the technology can be properly interpreted. All right, so that's our goal moving forward. So let's look at our first objective, testing a claim about a population proportion. We would like to be able to conduct a formal hypothesis test of a claim about a population proportion P. So just to put something in your mind when this says that from previous section, an example of a formal hypothesis test about a claim would be that you have a claim about the value of the parameter of a population. And since in this section we're focusing on proportion, we can use like the example we did before. Let's say our claim is that of the student population at DVC, more than 20% of them will wear at least one article of clothing that is blue in color. A nice example offered up by a student yesterday. Is that you, Zach? I forget. Anyway.
Thanks.
So let's go forward with that. So you could have as an example that you have the claim is that P, the population proportion, in this case of people wearing a blue article of clothing, is greater than 20%. And that we would want to have the objective of conducting a formal hypothesis test of this claim. And the way we would conduct a formal hypothesis test is we would produce a null hypothesis and an alternative hypothesis based on this claim. The null hypothesis would be where you set the parameter equal to the value in question. So in this case, it would be that the proportion is equal to 20%. And the alternative hypothesis would in this case be our claim that the proportion is greater than 20%. So with these formal null and alternative hypotheses in place, we would then take a sample of the population, and based on a particular test statistic for our sample, we would look at the p-value of that test statistic, which is the probability that we would get that kind of a result if the null hypothesis was assumed to be true. In this case, that the proportion really was 20% and that our claim is wrong. And then if the p-value is very low, meaning lower than some significance level, some alpha level, like 5%, that would suggest that the probability that our sample would come out the way it did if the proportion was 20% is very low. And since the probability is very unlikely, given that it's 20%, we then say that that is evidence that actually it's not 20% and that we reject the null hypothesis and instead support the alternative hypothesis. All right, so let's see how the slides would take us forward. So they introduce a bunch of notation, and I'm going to skip this because I think we know the notation we need, and we're not going to be doing any formula use. So anything like that, I'm going to skip. So let's remind ourselves when we have a population proportion test. So here are some requirements, and they're focusing on the normal approximation method, meaning using normal to approximate a binomial. But proportion does have the same characteristics as a binomial distribution, so we can focus on those characteristics. So what do we mean when we say proportion again? It means some portion of the population, some percentage, falls into a particular category. And the simplest way to think of that is all the people who would be successes in a binomial distribution. So that's why a binomial distribution works perfect for a proportion claim. So for example, I could ask the students at DVC whether they are wearing a piece of blue clothing, or I could observe them and mark off if I see that one of their pieces of clothing is blue. And so then there will either be a success or a failure, which matches with our binomial requirements. Sample observations are of a simple random sample, and the conditions for a binomial distribution are satisfied. There's a fixed number of trials. That would be the number of my sample. The trials are independent. If one person has blue, that doesn't change the probability that the other person, next person, would wear blue. Each trial has two categories, success and failure, wearing blue or not. The probability of success remains the same in all trials. The chance of picking somebody who's wearing blue is just based on what proportion of the population is wearing blue. And that stays the same every time you pick somebody. Again, the goal for that is that if you have a small sample compared to the size of population, you can act as if that is with replacement. So removing one person with blue clothing doesn't change the odds that the next person you pick will also have blue clothing. So that means you can act as if it was with replacement. So again, lots of concepts from the past piling up in here. Maybe some of them are clear, maybe some of them have been forgotten. But nonetheless, the basic idea behind a proportion from a population is what percentage of the population fulfills a certain criteria, either is wearing an article of blue clothing, calls themselves a Democrat, things of that nature. All right, so that's when you have a proportion distribution. And here, the third condition is the idea that the sample size is small enough so that you can kind of act like it's assumed without replacement. Then they give you a formula for a z-score, which we're not going to use. So then they talk about the two ways we can begin to work toward our objective of testing this claim with a formal procedure, a hypothesis test. There's this p-value approach. Don't erase anything. And then there's the critical value approach. We looked more at both of these last time. The critical value idea is that you find the critical value based on your significance level, and then you check the distribution score. For a proportion distribution, it would be a z-score. You check the z-score to see if it falls in the critical region. But it's much simpler to have StatCrunch tell you what the p-value is of your statistic and just compare that directly to the significance level. So I think that's why the p-value method is simpler, and it will be a little bit more natural and easier to learn. And so I want to focus on that and suggest everybody start with that. And then once that gets comfortable, you can then go and see how the critical value is just a slight tweak on that method and is kind of a similar thing. But the p-value is a better way for us to start. And as I said, I think the p-value will get you through the majority, if not all, of the problems on your assignments. So then there's this other method they talk about, the confidence interval method, and it is not completely equivalent in all cases with the p-value method. And again, this is getting a little bit further into weeds than we're ready to think about right now. They do have a recommendation here at the end: use a confidence interval to estimate a per population proportion, but use the p-value method or critical value method for testing a claim about a proportion. So yeah, confidence levels are good to just give you an estimate. If you don't have a claim, if you don't have an idea of what you're testing, then just produce a confidence interval and you'll get a range of values in which you have a good certainty that the range of values contains the population value. But if you have a specific claim, p-value method is what you would want to use, and that's their recommendation. All right, so now we've got an example with 16 slides. One of 16 slides for this example. And this is an example that they began to introduce to us earlier, the idea of consumers being uncomfortable with drone deliveries. So we've worked with this a little bit last time in 8.1, but now we're going to be very careful and look at how to perform a hypothesis test to test a claim. And I think there's so many slides here partially because they're going to go over all the 3 different ways they talked about, and we're going to focus on the p-value. So let's do that. So again, what was the situation? You have 109 consumers were asked if they're comfortable with having drone deliveries for their purchases, and 54%, or 545 of them, responded with no. use these results to test the claim that most consumers, and as you may recall, that means greater than 50% or greater than a proportion of 0.5, that most consumers are uncomfortable with drone deliveries. Now, again, here's the idea of the difference between what you just look at your sample and what some simple common sense might indicate compared to what a rigorous hypothesis test will do for you. Well, in our sample, we got more than 50%. We got most of the sample felt that way because it was 54%. But the thing is, it's not a lot more than 50%. And so because the results of our sample do have a certain randomness to them, because the 109 consumers were just randomly chosen, well, if the population proportion was exactly 50% and not greater than 50%, well, half the time you're going to get a random sample with more than 50%. Half the time you'll get less, and that's why it would sort of average out to a proportion of 50% if that were the true population proportion. But that would suggest that half of the time your sample's results might be misleading. If you think that every time you get a sample, you're more than 50%, that sample is then telling you that you should believe the population proportion is more than 50%, because it might not be. Even if it were 50%, that would happen half the time anyway. That would be very common. That's not very good, certainly not sufficient evidence. So the question is, when you're up at 54%, is that higher enough of a value to start to be more convincing? And that's where the hypothesis test comes into play. So having sort of tried to describe that idea of how a hypothesis test is looking for more clarity than just looking at a point value from a sample can provide, we begin by looking at the requirement tests to test using our methods that we've been discussing. First of all, it is a random sample. If you have a bad sampling data, then the results are going to be bad as well. And the golden rule for statistics is to properly reflect what's going on in the population. You want to choose from the population in as random a way as possible. You don't want any biases in your sampling methods. 2, there's a fixed number of independent trials. So these are some of the conditions specifically for a binomial distribution, which we're going to approximate with a normal distribution. But at the same time, to test for a proportion, we do want to have some idea of successes and failures, and we're going to have some fixed number of people in our sample. So in this case, there's 1,009. Requirement 3. Again, this is the requirement you want to double check to make sure that you can use the binomial distribution idea. And so there was a little description of the idea that the number of people in your sample times the probability of a success and the probability of a failure should always be more than 5, that you don't have some extremely rare thing you're examining with not very many people. So that's what this third requirement is indicating. But these are all satisfied. So now what they're doing right away is they're talking about using technology to help you do the p-value method. And this is what we're going to be doing. So this is a nice reflection of the place we want to begin understanding the procedure for a hypothesis test, which is where you set up the test, you know what the test is, and then you use technology to give you some results from your sample. And as we saw in the first section, what they are highlighting from the technology is 2 things. The test statistic, which in this case is a z-score because we're using a z distribution, and the p-value that we've been talking about. The p-value is right there. So computer programs and calculators usually provide a p-value, so the p-value method is used, and that's why I'm emphasizing that. And we'll get the same thing from StatCrunch. So let's look at this p-value method. So if technology is not available, it is. We would use a table, but we're not going to worry about that. Step 1, the original claim is that most consumers are uncomfortable with drone deliveries. And that claim can be expressed in the symbolic form, P is greater than 0.5. This step is equivalent to what we were discussing earlier, where I was saying, here's where we're going to go. And I said, our claim is that proportion of people wearing an article of blue clothing is greater than 20%. And in this case, it's that the proportion of people who don't like drone deliveries is greater than 50%. That's the claim. So then you want to be able to, from the claim, come up with the null and alternative hypothesis. And as we discussed in a little bit more detail in 8.1, you move toward that process by recognizing what would be the opposite of the claim. And remember, your claim has to always be greater than, less than, or equality. And so then in this case, we have a greater than claim. And then the opposite of that would be less than or equal to 50%. In other words, if the proportion of people who don't like drone deliveries is less than or equal to 50%, then our claim is wrong. Then it's not more than 50%. It's not a majority. We're uncomfortable with that. So with those two things in place, you can then define your null and alternative hypotheses. The null hypothesis will always be where the parameter, in this case, the proportion, is equal to the value in question. And our value in question here is 50%. And then you would choose for the alternative hypothesis greater than, less than, or not equal to based on the original claim. In this case, the original claim is greater than, so that's what we choose. So we are able to set up our null and alternative hypothesis. And so setting this up still is something students are starting to see what to do, but they often still don't understand what it means. I'm going to try to illustrate this in a second. Let's see if the next slide is the place to do that. I think I'll wait just a second, then I'll draw a picture. So for the p-value method, now that we have a null and alternative hypothesis, we need to have a significance level. We need to know with what assurity do we need to feel comfortable in order to make the claim that, or in order to support our claim, in order to say that our sample evidence supports the claim of being greater than 50%. And so the significance level is this alpha. And again, the alpha level means we want the percentage value of alpha, in this case 5%, to be the probability where we believe that in order to support the claim that the proportion is greater than 50%, that the chance that we would get from our sample a value as high as we did, greater than 50%, the chance that that would happen just randomly if we were wrong needs to be less than 5%. If the chance that we're wrong with this sample as evidence is less than 5%, then we say this sample is evidence that we're right. So the significance level is the maximum likelihood that we are wrong looking at our sample that we are willing to tolerate. And it's usually 5%. We're willing to claim from our sample, make a claim based on our sample supporting our greater than 50% claim, as long as the chance that we're wrong is less than 5%. We want to be 95% sure that it is good supportive evidence of our claim. Now it says because we are testing a claim about a population proportion P, the sample statistics P hat is relevant to this test, meaning the proportion of our sample, which was 54%. And we can use the sampling distribution of sample proportions. That goes back to the central limit theorem and our ability to use a normal distribution and all of those things that we've studied so far. All right, so then they use a big horrible formula. I'm going to ignore that. And then they do the solution. All right, so here, I'm going to use this picture here. So let's look at their solution, but there's a picture coming to help us understand what the heck is going on here. So they used a formula to get a z-score and a p-value and all this, just a z-score here. So then they looked up from that z-score on a p-value on a table, or you could do that with technology. But in the end, they got this. And I'm going to say we would use StatCrunch. So let's say you have your claim, you have your null and your alternative hypothesis, you have your significance level, and you have the results of your sample, which was 545 out of 1,009 people said they don't like drones, 54%. So if you have those things, then you turn to technology and it gives you a p-value. And so what does that mean? So what they're doing is they're looking at the mathematics of a distribution of samples of 1,009 under the assumption that p is 50%. So the math is based on using the null hypothesis. The null hypothesis is that p is 50%. So what they're saying is, if p is 50%, then the sample that we got, the chance that you would get the sample that we got, if the proportion of the population was 50%, is 0.0054. If the population is 50%, then the probability of getting our sample, which we did get, our sample results, is 0.0054. That's the thing to understand, what the p-value means. If the population proportion is equal to 50%, then the probability with our sample that we would get 54% is less than half a percentage. The chance that the sample would come out all the way up there at 54%, if the actual population's proportion was only 50%, is very low. It's about 1/2 of 1%. So that's very unlikely, like 1 out of 200 chance. So the idea is that if the probability that your sample would come out the way it did is really low, if that is really unlikely, assuming the proportion is 50%, well, that suggests that maybe the proportion is not 50% and that assumption is false and that you can reject that assumption, which is the null hypothesis. So you could say something like, since this is so unlikely, and when we say so unlikely, we mean less than alpha. In this case, it's way less than alpha. It's like 10 times less than alpha. Since this is so unlikely, we believe p is greater than 50%, not p equal to 50%. So we reject, getting sloppy trying to write on my tablet here. We reject the null hypothesis and say this is sufficient evidence, meaning our sample is sufficient evidence to support our claim, which is the alternative hypothesis. Man, this looks really sloppy. So again, one more summary of the idea here. So the notion is you have a claim, you set up your hypothesis test, you take a sample. You look at the p-value of your sample, which is the probability that your sample would come out the way it did if you assume the null hypothesis. And if that probability is very low, it causes you to question your assumption. You say, well, I really feel it's really hard to believe the proportion is 50%, when there's less than a 1 out of 200 chance that my sample would come out at 54% if it was. So I think this is evidence that actually the proportion is not 50%. And this is evidence in support of my claim that it's more than 50%. And that's why my sample came out at 54. Because the actual population proportion is really more than 50. You're not even saying how much more. You're just saying this supports the claim that it's more than 50%. All right, so that's the logic and the key in a nutshell, as well as the procedure that we'll use. So as they describe here, because the p-value is less than or equal to the significance level of 5%, we reject the null hypothesis. We reject the hypothesis that the proportion is 50%, and we support the alternative hypothesis, which was our claim, that the proportion is greater than 50%. We conclude that there is sufficient sample evidence to support the claim that more than half of consumers are uncomfortable with drone deliveries. So if we, in general, again, this, as I discussed in the 8.1, this conclusionary statement there is key to understanding what that means. And the way we get this is, remember, if the p is low, the null must go. If the p is low, the null must go. And so then they're going to do example of this same thing using the critical value method, and then they're going to use an interval method. And I'm going to instead stop the slideshow here so we can look at some examples focusing on the p-value approach, because I think that's the easiest to understand. And I think that will get us through most of the problems. So I'm hopping over to take a look at our homework. And so we would be on assignment number 10 for our homework. And so this is on 8.1 and 8.2. The first half of the problems are on 8.1, something like that. And then the latter ones are on 8.2. So I'm going to jump down maybe to number 38. Let's see what we got here. Okay, so let's, well, this one's a little wordy. Let me find one that's just not much to read and a little simpler, if there is such a thing in here. It just seemed to get wordier and wordier the farther I go. What if I'm like a number 20? That's still 8.1. Oh, so it looks like 8.2 doesn't start until number 26. And then they have one where they show you technology, another one like that. But I want to do one where we use StatCrunch. All right, so let's try number 29. This isn't too wordy, and it looks like we have to do it ourselves. Okay, so in a study of the accuracy of fast food drive-through orders, which we've looked at before, one restaurant had 39 orders that were not accurate among 327 orders observed. use a 1% significance level. Notice they've lowered this down to be less than 5%, but again, you can make it whatever level you want. That just depends on how sure you want to be about your conclusion. Use a 1% significance level to test the claim that the rate of inaccurate orders is equal to 10%, meaning that's the proportion that we're testing a claim of. Does the accuracy rate appear to be acceptable? Okay, so so the very first thing they ask is to identify the null and alternative hypothesis. So let me look at this. Excuse me. So again, we are testing, they tell us, test the claim that the rate of inaccurate orders is equal to 10%. So that's the claim that's being made. And so then we can imagine that as the claim is that the proportion is equal to 0.10, 10%. That's the claim. So then from that, we want to construct our null and alternative hypothesis. And so the null hypothesis is always when you are setting the parameter equal to the value in question. So that would be that P is equal to 0.10. And notice for this problem, the null hypothesis is our claim. Is our claim. So then the alternative hypothesis, and the alternative hypothesis will be either less than, greater than, or not equal to. If your original claim is a less than or greater than, then that's the null hypothesis. But if your original claim, then that's the alternative hypothesis. But if your original claim is the null hypothesis, then the alternative to that is simply not equal to what your claim says, in this case, 10%. So in this case, our null hypothesis is that the proportion of inaccurate orders is 10. And our alternative hypothesis is that it is not equal to 10%. And that is, looks like number 1 here. Questions about how I set up the null and alternative hypothesis based on the claim? Okay, so now that we have that, we then, as I was just illustrating in the slideshow, we would then perform the hypothesis test by taking the results of our sample and coming up with a p-value. Now, they're asking for the test statistic, which is also provided by StatCrunch. So in either way, we can do that in StatCrunch. So I'm going to open up StatCrunch. And I'm going to go to stat, and we are doing a proportion. So I'm going to do proportion stats with one sample. And I think there we go. With summary, because they just tell us a summary of the results. So the number of successes, in this case being inaccurate orders, was 39 amongst a number of 327 observations. And now we've already set up our null and alternative hypothesis, so we can provide those to StatCrunch. And we have the default of 50%, but I'm going to change that to 10% for the null hypothesis. And in this case, the alternative hypothesis is then correctly written as greater than 10%. If we needed to change it to less than or equal, or greater than, less than or greater than, we could do that here, but it is by default what we want, which is that P is not equal to 10%. And that's it. We've given the results of our sample. We've told it the hypothesis test that we're making, and we compute. So here's where technology is providing us with the test statistic, which in this case is a z-stat, and the p-value. They ask for the test statistic. So I'm going to get that to, looks like 2 decimals, which means I do not have to round up. Then they want the p-value, and they want that to 3 decimals, which I do need to round up. Okay, so now the thing is to draw the conclusion is we'd like to have some idea of what that p-value means. So the p-value is the probability that we would get the sample the way they did if the null hypothesis was wrong. So our null hypothesis, which is also summarized in my little StatCrunch box here, the null hypothesis was that the proportion of incorrect orders is 10%. If that were the case, what is the chance that our sample would come out the way it did? Well, it's 25% almost. It's almost a 25% likelihood that you would get a sample the way we did if the order inaccuracy was at 10%. And that's very possible. 25% is not a low probability. That is not a rare event. That's going to happen like 1 out of 4 times. And so in general, we compare the p-value to our significance level. Well, our significance level for this problem was 1%, and we got closer to 25%. The p is not low. The null cannot go, therefore. That means this does not provide sufficient evidence to reject the null hypothesis. This is not very good evidence that the percentage is not 10%. So we fail to reject that null hypothesis because the p is not low, not even close. So of our choices here, there's 2 that say fail to reject, B and C. One says you're failing to reject because there's not sufficient evidence to warrant the rejection. The other says we fail to reject because there is sufficient evidence to warrant rejection. Well, that doesn't make any sense. If there was sufficient evidence to warrant rejection, why are we failing to reject? So part C doesn't make any sense at all. Therefore, the answer is part B. And let's read it out thoroughly. We fail to reject the null. There is not sufficient evidence from our sample to warrant rejecting the claim that the rate of inaccurate orders is 10%. Why? Because if that were the case, that it was 10%, this would be a very common result. This is not unlikely. This is not a rare occurrence. So it's not evidence against the null hypothesis. That's the logic. Questions about that? All right, so then they ask us a follow-up question because they are trying to have us think that the statistics helps us think about the real world and make decisions in the real world. It says, does the accuracy rate appear to be acceptable? So we're going to have to decide whether we think that's acceptable. Then it does have things that we can eliminate right away. Since there's sufficient evidence to reject the claim, there wasn't. So we can ignore A. Since there's sufficient evidence to reject the claim of the rate is equal to 10%, there wasn't. So it's going to be C or D. And then we just look at what they say after that. Since there's not sufficient evidence, which was the case, to reject the claim that the accuracy is 10%, the restaurant should work to increase that rate. Why would you work to increase the rate of 10% inaccurate orders? So that just sounds silly. Since there is not sufficient evidence to reject the claim that the rate of inaccurate orders is equal to 10%, it is plausible that the accuracy rate is 10%. This rate would be too high. The restaurant should work to lower the rate. By common sense, hopefully that's D. Questions, comments, discussions about that at all? All right, let me skip to a non-equality one and then see if we can do one more. There's about 5 minutes left. See if we get another example in here. Wow, it looks fat. This one. All right, let's try this because this isn't too wordy. Suppose that in a random selection of 100 colored candies, actually, I think I'll skip this because I think I did this for you in our StatCrunch video tutorial. Looks familiar. Maybe that's why it was done. So let me try a different one. All right, let's try this one. So number 33, it says, suppose 201 subjects are treated with a drug that is used to treat pain, and 52 of them develop nausea. Use a 10% significance level, that's kind of a higher significance level, to test the claim that more than 20% of users develop nausea. Okay, so I'm not going to try writing this down this time, but I'll describe it and see if it makes sense. The claim is more than 20%, so the claim is P is greater than 20%. That means the null hypothesis is that P is equal to 20%, and the alternative hypothesis is that P is greater than 20%. That is B. Then we put this into StatCrunch. I've already got the right tool, so I'm just going to edit the results from before. So now we have 52 out of 201. And our proportion that we're testing is 20%. And our alternative hypothesis is that P is greater than 20%, which is now what we're claiming. So now in this problem, our claim is the alternative hypothesis. And we get this box of results. So they want the test statistic to 2 decimals, which is 2.08. And they want the p-value to 3 decimals, which is 0.019 if I round up. Okay, so again, now what we do is it was easy to set up the null and alternative hypothesis to give StatCrunch look at our sample and give us our test statistic and p-value. And the p-value is a little under 2%, and our criteria level for significance is 10%. So this is well under 10%. So the p is lower than the significance level. If the p is low, the null must go. That means we reject the null hypothesis. It's got to go. Our null hypothesis was that the proportion was 20%. So since we're rejecting that, this is therefore sufficient evidence to support the alternative claim, which was our claim, that the proportion is greater than 20%. So we want to pick that somehow. So the p was low, the null must go, so we reject the null, which is B and D. There is not sufficient evidence to support the claim? No. There is sufficient evidence to support the claim of more than 20%, because we're rejecting the null that it's 20% and supporting the claim of more than 20%. So that's D. And that's all I wanted.